So far, we've been dealing with what I would call the most straightforward connection between integrals and areas, because we've only dealt with positive functions. However, we start to see a bit of a deviation between areas and the integral value. They're basically equivalent when the function is positive. When we get into negative values for a function, take a look at this graph here, then, well, the area idea and the integral diverge a little bit, or you have to think about it a little more carefully. So let's take a look at a curve here, a function of time, that has the graph shown below, and we've got these different areas, and what I would say here is that A, B, C, D, and E are positive areas. The way we talk about areas is always positive, right? I can't have a negative area, -2 square meters. That doesn't make sense. So on a graph, if we say area, we mean positive. Now, if we talked about making a Riemann sum, so that, again, Riemann sum is a sum of heights of the functions, or values of the functions better now. Let's do the left-hand sum, times delta x. If we looked at the rectangles we would build, some of them would belong to the region A, some to B, some to C, some to D, and some to E. All right, so we'd have that division, or those translations of the graphical interpretation of the Riemann sum. I'll put all the details in there. There we go. And, well, wait a minute. Some of those are going to have positive values. When f of x sub I is greater than 0, then it contributes a positive value to the sum. Or, because the sum and the integral are the same, except the integral has more and more intervals, those values contribute positively to the total integral. However, if we looked at any of the regions where the rectangles would be below the axis, what does that mean? In those regions, f of xi minus 1, those values that we're looking at, are less than 0. And what would they do? They would contribute negative values to the sum or to the integral. So, and let me just try not to make a false dichotomy here. We'll use the same subscript there. So the key point is sometimes the function is positive, sometimes the function is negative. When we're calculating a sum of the function values times delta x's, the sign really matters for that f. That's really what drives its contribution to that particular part of the sum. So how does that relate back to our integral here, where we have this entire area, and again, we think of A, B, C, and D, and E as positive areas? Well then, there's an easy part. The A, C, and E, the integral from A to B of f of t dt. Let's actually do this in detail. Oops. Let's try to do this in detail. That is, by definition, the limit, as the number of intervals goes to infinity, of the sum of f of xi minus 1. Let's do left-hand sums, that's fine, up to n, starting at 1. So again, here's those values of the function that play a role in the overall sum or in the overall integral. Well, for sure, when we look at the rectangles that define A, they're going to add up, and we're going to get positive things there, positive area, fantastic. When we see the values in the region C, all those function values are positive, we get nice positive values, we get the area under the graph, we've seen that. Likewise for E. But when we talk about B and D, we just have to remember the area in terms of its absolute value would be the same as if it was above the graph, or above the x-axis rather, but the function values would be negative. And if the function values are negative, they're going to offer a negative contribution to the integral, or to the sum, whichever way you want to think about it, is less than 0 on these intervals. And so we have the same idea. Somehow the integral and the area are closely related, but if the area happens to be beneath the x-axis, it contributes a negative amount to what we call the integral, because we'd be adding up negative things, and if we add up negative things, we get a larger negative number. So that's one way to think about, or to tie in, the idea of the definite integral to negative parts of a graph, and the area underneath the graph, to generalize that to negative portions of it. It's important to think of a physical example as well. If f of t was a velocity, then what would the negative areas represent? Well, let's go back to the positive areas. Those would be distances traveled. Let's try to write that legibly. Distances traveled. If v is positive, that would mean in the forwards direction. And if we had the negative areas, or the areas, more importantly, areas with negative velocity, that's really what we're talking about here, those would be distances traveled. Take a big guess. Instead of being forwards, those would be distances traveled backwards, or to the left, depending on how you set up your axes. Let's say right or left. Those would be the two most common ways to define positive velocities and positive displacements. So there's nothing unusual about having negative parts of an integral when we're talking about the function representing velocity. When we talk about areas, okay, then we have to think, why would we ask the question, do we want this to be positive? Do we want it to be negative? Is an integral exactly what we need? But in many physical scenarios, and certainly finance, biology, everything else, this negative idea, the option of having negative function values and adding up their contribution to a total, is entirely natural. It's nothing we should avoid at all or worry too much about. In fact, it usually captures exactly what our intuition represents. It's only when we think of areas, actually, that we get into some potential intuition breakdowns, when we have positive and negative contributions to an overall integral.